Hello, and thank you for joining us today. Today's webinar is Analysis of Bottled Water by Teledyne Tekmar's Fusion, presented by Joy Osborne, our TOC Product Line Manager. We will be taking questions, so feel free to submit them throughout the presentation, and we will address them at the end of the slideshow. Okay, Joy, I'm going to turn it over to you.
Thank you, Shelley. Like Shelley said, today's presentation will be on the analysis of popular bottled water using Teledyne Tekmar's Fusion. We took 5 popular bottled water brands that you have probably all seen on your grocery store shelves, and then we analyzed them for total organic carbon content, or TOC content, as an indirect means of cleanliness and purity. To differentiate the various brands of bottled water, we disclose the source of the water, like if it came from a well or a spring, that kind of thing, and then its cleanup technique. Jeremiah Bradley was the application chemist on this study. Please note this is a live web presentation, so please forgive me if I need to take a pause, like a drink, or mispronounce something. All right, so today's agenda will discuss TOC's importance to drinking water. So why we chose TOC over other techniques. There are other techniques you can use for contamination. About the fusion and why it was chosen for this application, being bottled water. And then the test plan for the bottled water, including methodology, standards, sample prep, all that kind of stuff. And then we will reveal the TOC results of each bottled water sample. All right, so let's start with why TOC analysis was chosen to compare the cleanliness or purity of bottled drinking water over other contamination analysis techniques. So let's start with why TOC is important. The raw water used to make drinking water is initially tested for TOC content to benchmark to ensure the cleanup process is effective. So they can take a measurement from the beginning of the process and compare it to the end results to make sure it's drastically reduced from the cleanup process. The raw water is then filtered and tested again for TOC content to verify it is not too high, since carbon in the water, when disinfected with a halogen like chlorine, which is the most common disinfectant process, chlorination, will form trihalomethanes, which are these type of compounds. The problem with these compounds is they are known to be carcinogenic. Therefore, they are a public safety concern. If it is too high in TOC, they will filter it again. Then once it's at a safe starting point, they will disinfect it with typically chlorine, although there are, other techniques they are developing across the country and the world. After the disinfectant process, TOC is measured again and recorded in a public quality water report. Typically, drinking water you get from the tap is around 1 to 3 parts per million. Of course, that can vary depending on your piping and all that kind of stuff too. Okay. All right, so here's an example of Cincinnati's water quality report from 2018. So I use Cincinnati, Ohio, because that's actually where we're located, Teledyne Tekmar. So this is the water that I drink. Please feel free to check out your own area's quality water report. Please note that the trihalomethanes, the highest compliance level detected in our water was 56.5 units, which is under the max allowed limit of 80 units, which I assume the units is in parts per billion. So if you see here, the maximum allowed is 80. The highest they detected in 2018 was 56.5. And remember, this is a byproduct of chlorination, and again, it's a public safety concern because it's a known carcinogenic. Okay, and then a lot of municipalities and areas also report a TOC measurement. There is no defined maximum. Again, it's an indirect means of determining the cleanliness or purity of the water. So obviously, the lower, the better. So they actually don't put a max amount allowed in your drinking water, but it's good just, again, as a reference of how clean that water is. So the water we drink here in Mason, Ohio is about 2 parts per million, was the highest that they recorded. This is done by state regulations. For example, I know Ohio and Kentucky require TOC content reported publicly like this, while Michigan does not. So you might have to check with your local area, state, or country on if it's required or not. Okay, so why would you choose TOC over other techniques for contamination readings? So obviously you could use a variety of chromatography methods. HPLC, GC, NDIR are all techniques used to find contamination in drinking water. The drawbacks to these instruments is they're typically much more expensive than a TOC analyzer, especially if they have a mass spec detector on them. So, and with that, they're usually highly technical, and you have to develop a method. Let's say you're developing a method to see the pesticides. You may have to actually develop several different methods just to see pesticides or something along that by HPLC. So you're not able to see a variety of things in one analysis. You see specific analytes that you're targeting. So you may not even know to target certain analytes that are in your drinking water. So it's, you know, a very selective analysis. On the other hand, TOC is relatively inexpensive in comparison. It's very easy to operate. You know, you don't need to be a PhD chemist to develop the methods for it. In fact, you usually can use, well, I would say 95% of the time, you usually use the methods that are already pre-programmed into the analyzer, so you don't really have to develop any method. And then it's a great catch-all method. And by catch-all methods, you're probably wondering what that means. Most drinking water laboratories use TOC over other analysis types like HPLC, GC, because it is a catch-all method, meaning it picks up a lot of different contaminants in one reading. So chromatography, again, usually only you can see one or a few different analytes in one test, while TOC you can see cleaning agents, bacteria, a lot of different solvents, pollutants, fertilizers, pharmaceuticals, pesticides, organic matter, so like agricultural runoff, that kind of stuff, and a lot more. So again, in one test, you can see a variety of different types of compounds. All right, so now we'll talk about why we use Teledyne Tekmar's Fusion and why it was selected for this bottled water application. Okay, so just to get started, I want to give you some background on the Fusion. So these are the specs. Analysis time is typically 5 to 7 minutes for each replicate. So again, it's really fast. Carryover is less than 1%, and it actually has an automated rinse process between each replicate. So we'll take an aliquot of DI water and rinse the entire sample pathway to help reduce any kind of carryover from sample to sample or rep to rep. The range of the Fusion, it can do 0.2 parts per billion. Now that is a MDL, it is a minimum detection limit, which means it's a theoretical value. If you want to learn more about that, there's actually a webinar on detection limits on YouTube that we made. It's just basically saying 50% of the time you'll be able to pick this up as a reading at this level. So half the time you run a 0.2 ppb sample, the Fusion will pick it up. It will integrate the peak basically. And it will go all the way up to 4,000 ppm. That is dilution dependent. The Fusion is capable of diluting up to 1 to 200. It can do a variety of different modes. It can do total carbon, total organic carbon, total carbon minus inorganic carbon, which is what is used in Canada as their standard method, just inorganic carbon, and then we have an optional accessory for purgeable organic carbon. The precision is very precise. It's less than 1% for a mid-level standard, And you can play around with the sample size from 2 to 10 mils when you're developing a method. You would want to use a larger sample size for lower level of TOC. So if you're using a 9 or 10 mil method, this is very low analysis, like drinking water, pharmaceutical water, that kind of thing. The methods it complies to is EPA methods 415.1, 415.3, 96A, standard methods 5310C, ASTM D4779 and D4839, and then these pharmaceutical methods, which are cleaning validation, USP 643, which is a system suitability test, European Pharmacopoeia 2.244, and Japanese Pharmacopoeia. So the applications we recommend for the fusion is drinking water, water for injection, purified water, and semiconductor manufacturing water. So typically pretty clean applications. It can, like I said, go up to that 4,000 range, but then you're going to introduce a dilution. Okay. And there are some options with the fusion. Basically, there's 3 different autosamplers you can select. The most standard one is the 40 mil 75 position, but you can use a 90 mil 90 position 55 mil vial or 120 position 20 mil vial. What I want to point out is that there's 4 positions in the middle that you can put stock standards in, or continuous check standards, or reagent water, or whatever you want that you would run over and over again in these slots. And then if you take a stock standard, the system will auto dilute it for you, or it has a feature called auto calibration, where it takes a stock standard, it does serial dilutions, like I said, up to 1 to 200. So you actually only have to make 1 standard up. You don't have to make your full calibration range of standards. It will automatically do that for you. And it does it very accurately. Another thing I like about the fusion is all the glassware is on the front of the fusion. You can see it through this tinted panel, basically. This allows the user to know immediately if something is wrong with the instrument. If something isn't draining properly because there's a restriction, or if a liquid sample gets stuck in one area of the glassware, let's say the IC sparger is not draining, that kind of thing. So you'll know immediately if there's something wrong. Also, if your sample contains halogens, you will see the copper side of your halogen scrubber turn brownish color, just like a penny would with oxidation kind of thing. So it's important to remove the water, which is what the mist trap does, and halogens, which is what the halogen scrubber does, because those are 2 things that can damage your NDIR detector, which is by far the most expensive part on the instrument. So you want to be able to monitor these things, making sure there's not water getting the detector or halogens getting the detector. So it's good to be able to see them. So they're right there. All right. So if you take off the left side panel of the fusion, which is only a few screws, you'll see there's a few other parts. Here's our mass flow controller, which enables features like auto leak checking. So if you do happen to get a leak in your system, you can just hit a button in the software and it will leak check it for you. And it will even break it up the sample pathway into 2 different ones, so you can kind of devise from there where it is. There's also a perm dryer, so this gets the rest of the moisture. The mist trap gets most of it, and then the perm dryer gets what little moisture is left, again, to protect your NDIR detector. And then here's your NDIR detector. The Fusion software has many workflow easing features. It's a tool for 21 CFR 11 compliance. If you don't know what that is, it's basically standards used in the pharmaceutical industry that mandate you have to have electronic signatures, you have to have auto archiving of data so you don't lose it, that kind of thing. So those are already built into the software. You just have to enable them. And then we have a feature called IntelliDilution, which is also really nice from an analyst standpoint. So if a sample is above the calibration curve range, so let's say your calibration curve goes up to 10 parts per million, but your sample is 13 or more, or something like that, it will actually flag it, dilute it back down into your calibration range for you, and keep running. So if this happens overnight, you'll still have results in the morning. So you don't have to worry if you have an occasional sample that's above your calibration range. It is Windows 10 compatible. I get this question a lot. That's why I include it. You know, they're not making Windows 7 computers anymore, so it seems like everyone that's looking at a Fusion is asking if it's Windows 10 compatible. I just want to confirm that it is, in fact, compatible. It has this great benchmarking tool. So it basically checks almost everything on the instrument. You know, it'll check the Autosampler for movements, the lights on the front, it will leak check it. It will do all these kind of things to help you troubleshoot in case there is an issue. There's also a calibration editor, so you can make up several different calibrations with different methods in the same schedule. So let's say you run really clean samples, but you also occasionally get dirty samples from you know, a certain customer. You can have two different calibration curves in one schedule, and you can identify which calibration curve you want it to use. It has user access permissions, which is also part of 21 CFR 11. This basically enables different levels of users. So you'll have like a power user that can do everything. They can edit a method, edit a schedule. They can really play around with the software. And then maybe you'll have somebody that's not experienced, that you want it to be a basic user that can only start a schedule. You know, they can't accidentally change a method along the way or something like that. All right, so here I'm talking about why we use UV persulfate oxidation for drinking water. So that's, again, what the Fusion uses. It uses UV persulfate oxidation. So comparing the four main techniques, there are a few other ones out there, but they're not as common for TOC analysis. I chose UV persulfate since it has a very low detection limit. Like I said, so if you compare them, it's 0.2 ppb, 50 ppb on combustion. It's 0.03 ppb on membrane conductivity, yet it only goes up to 50 ppm, so there's a lot smaller window, and the same with a spectrometer, sorry, 0.3 to 20 ppm. The other thing I like to always consider is interferences. So what actually interferes with the detector that could give you false high or even more worrisome false low TOC concentration. So as you can see with an NDIR detector, the only two things you need to worry about are sulfur and halogen. There's a built-in halogen scrubber in all our instruments, and we offer an optional sulfur scrubber, so you can say with certainty that you're not going to get a false high reading from these compounds. With membrane conductivity and spectrometry, there's a lot more interferences, and again, a lot of them give you a false low result, meaning your sample could have 5 parts per million of carbon, but it's reading that it's 2 parts per million, so you think it's okay, but it might not actually be. So with membrane conductivity, anything that would affect the conductivity of the sample, so ions, salts, particulates, acids, bases, if there's anything like that in your water, it will give you an incorrect reading. Same thing with spectrometry. You'll have sulfur, chlorine, magnesium, calcium, which is common in tap water, things like that, magnesium, copper, and iron, and many more things that interfere with your results. So since combustion and UV persulfate both use an NDIR detector, I looked at which one has the least amount of background carbon. So you do with combustion, so the oxidation technique there is you're using a catalyst, which is typically platinum, 1% platinum on aluminum substrate, has some artifact carbon in it, meaning it gives off about 100 parts per billion of background carbon, while a UV persulfate only has a little bit of artifact carbon coming from its reagents. So it's sodium persulfate, you know, phosphoric acid, those kind of things. So if you're trying to do really low level analysis, you really want to go with the UV persulfate oxidation technique over the combustion technique because of the background carbon. And you can see the first three techniques are relatively the same analysis time-wise, except for spectrometry. It takes a couple hours. So it's a big, long process of sample prep and things like that. And then basically at the end, you just see how much the color changes after you do, you know, a titration, that kind of stuff with it. So it takes a long, long time. So that's another reason. Okay. And then I wanted to show you what's the difference. So we ran the same samples on an NDIR system versus a membrane conductivity system. So you can see it's 1 part per million carbon with 0.8% sodium chloride, and then 2 ppm carbon, 5 ppm, 10 ppm, 20 ppm. So the recovery rate for NDIR, it's slightly higher than 100%, but it's at least not a false low, and it's much closer. And the more carbon, the closer it is to what the accurate value is. So I wanted to show you how halogens interfere with membrane conductivity and why NDIR is the preferred technique there. All right, now let's get to how we established, now that we established why we chose the UV persulfate and NDIR analyzer, the Fusion for this application, let's set it up to run our bottled water samples. Please note that these images are not of the actual samples. This is just a generic picture. So the scope of the study was 5 popular bottled water brands were analyzing using Teledyne Tekmar's Fusion to determine TOC content as an indirect means of water cleanliness. All right, so the first thing I always do is start to look at the method. Even though it may not be the method you end up with, you know, you can get a good starting point. You know, I had enough knowledge to know roughly what tap water is, which is, you know, low ppm level. So I opened up our default TOC drinking water method, which is 6 ml sample volume. Our system goes from 2 to 10. And what I really love about the software is it already calculates the optimal sample range for that method. So this one goes up to 15 ppm and to 2.7 ppb basically. Okay, so I started to run this method and I quickly discovered that our samples were below tap water levels. So I went back and I changed the method. The first thing I did was increase the sample volume. So again, I went from 6 to 9 mils of sample volume. What you see here changes, it tightens that sample range so you can see lower levels better. So I upped the sample volume and then I actually reduced the acid volume. I believe the default's 1 mil, I did a 0.5 mil, and then same with reagent volume, I decreased that. And the reason I did that is because, again, these are really low level carbon samples. And there is a little bit of artifact carbon coming from your acid and your reagent, which is sodium persulfate in this case. So the less you use, the less background carbon you have to worry about. And there have been studies in the past to show that you can actually oxidize up to 1 part per million of carbon without the use of sodium persulfate. But you're welcome to try that yourself. So only UV light can actually, you know, oxidize maybe up to 1 ppm of carbon. And here's the standard preparation for this. You can purchase potassium hydrogen phthalate from any chemical vendor. We don't mandate that our customers buy our reagents or standards from us, so that way you can save money. So basically, to make a stock standard of 1,000 parts per million carbon, you fill a 1 liter volumetric flask, halfway with DI water, then you accurately weigh out 2.125 grams of KHP. You quantitatively transfer that KHP to the volumetric flask. You bring the volume with DI water, which means bring it up to the line. Shake vigorously and sonicate or mix for 5 minutes just to make sure it's homogenized. It should go in the solution very easy at 1,000 ppm. And then from that 1,000 ppm, you're going to make it a 2 ppm standard for this study. So basically, you take another 1 liter volumetric flask, you fill it halfway with DI water, and using a grade A pipette, don't use a grade B. We want it to be as accurate as possible. And I do like the to deliver ones personally. You pipette 2 mils of that stock 1,000 ppm solution into a volumetric flask. You bring to volume with DI water, which means fill it to the line. You shake vigorously and sonicate for 5 minutes, just again to make sure it's homogeneous. And then you can store that in the refrigerator for up to a week. So it is important, you do want to store in the refrigerator just to impede any bacterial growth. You can preserve it with a 1% phosphoric acid, which some people do, but if you do that, I recommend you reduce the amount of acid in the method. So if you're going to preserve it with 1% phosphoric acid, you're going to want to reduce this down because you already have acid in your method. Okay, so you don't have to worry about the inorganic carbon being removed. You already have acid in the matrix. Okay. All right, so let's talk about the sample. So again, we took 5 very common, I'm sorry, I'm not allowed to say which brands they are, but they're very common ones, and analyzed them. And we differentiated them by their source, so where they came from and their cleanup process. So the first sample came from spring water, and it used a 2-stage microfiltration and UV light cleanup process. The second sample also came from spring water, and it used a vapor distillation and cleanup process. And then the third sample, again, is spring water, which seems very popular. But this time it came from a natural aquifer. So it had, it was underground filtration type system. And then the fourth sample is from an artisan well water, so a special well of water. And again, it was cleaned up through an aquifer. And then the fifth sample just used municipal water, so basically our tap water. And then it went through a reverse osmosis stage. So if you want to take a second and just pause and kind of guess which one you think will be the cleanest and which one you think will be the dirtiest. I'll give you a little time to look it over, and then in a few more slides I'll reveal which one was the cleanest and which one was the dirtiest using TOC as an indirect means of measuring that. Okay, hopefully you have which one you think will be the dirtiest and which one do you think will be the cleanest in your head. Okay. Okay, sample preparation. There really wasn't any sample preparation involved. I just opened the bottled water. I filled a 40 ml BOA vial. I did want to note that we used the vials that were spec'd less than 10 parts per billion of carbon. Again, I'm trying to do really low level analysis. So if I can eliminate as much background carbon as I can, I do. So, I used the cleaner vials. I just inverted it 3 times to homogenize. It's probably not necessary. I'm sure it's pretty homogeneous already, but just as good laboratory practices kind of thing. And then after I opened it, I stored the bottled water in the refrigerator, and I gave it a 24-hour expiration. Please note that once you open the bottle of water, bacteria may grow, increasing the amount of TOC. Like I talked about earlier, TOC does pick up bacteria. So it's best to use a fresh sample when possible for the most accurate results. Acid will prevent this bacteria formation. So some labs, preserve it, like I said, with 1% phosphoric to extend the sample life. If you do this, we recommend reducing the amount of acid in the method parameters, okay? Okay, so these were internal testing criteria we used. We wanted to make sure all our standards, including calibration and check standards, were less than 5% relative standard deviation. And everything was run in triplicate. Our sample should be less than 7%. I'll explain that a little bit more later, why I didn't pick 5% for that. And again, we ran it in triplicate. So those are my precision criteria. And then for accuracy, I wanted my check standards to be within 10% of the actual value. And then the R-squared value of the calibration curve, I wanted to see at least 3 nines. Some SOPs say 995, some say 3 nines. Again, I was trying to look for very accurate results, so I went with 3 nines. Okay. Okay, so now let's get to the fun part, talking about the T results of each bottled water sample. All right, so here are the calibration results. So you can see we took a 2 ppm stock standard, which I explained how to prepare earlier, and the system diluted it for us. So it did a 1 to 2, a 1 to 4, a 1 to 10, a 1 to 20, a 1 to 40, a 1 to 75, and then a DI water, almost like a blank for this one. Okay, and then it calculates for you what the final concentration is. So we actually did a range of theoretical 0, or you could say accurately, 27 ppb to 2 ppm. And the reason I wanted to run a 0 again is we're doing really low level analysis, and I wanted to make sure the 0 came out lower than the 27 ppb, which it did. So here's the absorbance count. The theoretical 0 is 3.5, so it does give you some absorbance reading. So keep in mind there is artifact carbon, pretty much in everything, so there's going to be a little bit of a reading. And then the 27 parts per billion was 4.8 ABS counts. And then you can see the relative standard deviation. All except for the 0 are, definitely less than 5%. And then here's the date we ran it on. So the reason the 0 is a bit higher is because it's such a small absorbance count comparing it to, other 2 very small absorbance counts, meaning the numbers are so low. When you do an average and a standard deviation of all 3 numbers, it's going to seem high, but it's just the nature because of the sample, because it's so low to begin with. All right, so if you graph these all out, your y-axis is your ABS counts, and then, if you graph them all out, you'll get an R-squared value of 3 nines. Remember that of over 3 nines, that was our testing criteria. We actually got 0.996 for R-square value, so very, very linear from this in this range. Now, if you want with the software, you can always drop. If you didn't like the 0, you can always go back and drop the 0. This would actually most likely make this number higher. Again, I just wanted to verify that the DI water came out less than the 27 ppb to make sure we can at least identify 27 ppb that low. Okay. All right. So we recommend running check standards at the start and the end of a sample schedule. So we ran here's the concentration. This is like just pulled it directly from a report. I just snipped it and pasted it on. So we ran a 0.2 ppm or a 200 ppb check standard. And our criteria was plus or minus 10%, which would be 0.18 to 0.22 ppm. And it automatically tells you pass or fail, which it passed. It was at 0.1859. And we ran it in triplicate again, and the RSD was much less than 5%, 1.44%. And then at the end of the sample schedule, we ran the same standard again. Again, testing criteria was plus or minus 10%, and it came out 0.189, which was well within the range. And this time the RSD for the triplicate was 0.46. So again, very accurate, precise results. And from this, is the check standard is within 10% at the beginning of the sample schedule and at the end of the sample schedule, you can pretty confidently conclude that the sample results in between are within 10% accuracy. So that's why I always run it before and after samples. Some labs will run it like every 5 samples just to verify the calibration curve is holding. I only ran 5 samples, so I didn't really need like several check standards. But if I were to run more, I probably would do every 5 samples. I would do a check standard, or every 10 samples do a check standard. Okay, and a nice thing too about the software, if it did fail, which it will turn red, you can do a corrective action thing in the software if you want. You know, if it fails, you can have it recalibrate itself or rerun a check standard. Again, that way, if you're running it overnight, you'll still have results in the morning, even if your check standard fails. You can have it recalibrate and start again. So that's a nice option there too. All right. So this is, again, a snip of a report. So we ran the samples. I did scratch out their names because I'm not allowed to reveal what they are. So I just, wanted to note the RSDs. Everything was run in triplicate. So these are the 3 reps, and this is your percent RSDs. So the first, sample was 0.54%. The second sample was 3.04%. Third sample was 4.19%. And the fourth sample was 3.41, and then 5.36. Now this one's a little higher than 5%, but if you look at it, it's a very low level. It's actually, it's only 93.4 ppb, so it's the lowest. Which brings me to, if you had wrote down which you thought was the cleanest and which one you thought was the dirtiest, brand 5 was actually the cleanest. And after I sat down and thought about it, it did make a lot of sense. So, you're taking tap water, which is typically 1 to 3 ppm, and you're doing a very strong cleanup process, reverse osmosis. So I could say with confidence that's probably a very good cleanup, a very clean bottled water sample. Now, the first one was the highest. It was actually 1.4 ppm. So we're not even we're in tap water range now. So what I really found surprising was the disparity from brand to brand. So there's such a big difference in TOC content from each bottled water brand to the other. So, you could extrapolate from this. It's not really a large enough sample study, but you could say perhaps that, they are typically cleaner than tap water, bottled water, so you are getting a little more bang for your buck. You're not just paying for the bottle, you might actually be paying for a cleaner water for you to drink. Again, though, more testing would be needed. I would like to do like several different lots and all that kind of stuff, but that would take months and months. So this is just to show you a little sample of what kind of testing you can do with the Fusion. Okay, so the spring water with the 2-stage microfiltration and UV light process was you could conclude for this sample, this very sample, was the worst. It had the most TOC. All right, so here are the key takeaways I hope you got from this presentation. So just to recap, I hope you walk away with at least this much information. TOC in drinking water, so it's an indirect means of measuring water cleanliness. It's a good catch-all method because it catches a lot of different types of contamination. It's fast, typically 3 to 7 minutes per sample replicate. And then the different TOC techniques, if you remember, I compared the different ones. There's 4 primary types: combustion, UV persulfate, membrane conductivity, and spectrometry. UV persulfate was chosen for this application because it had the fewest interferences. In fact, all the interferences that you would have to worry about have scrubbers. You don't really have to worry too much about it. There's also a lower amount of background carbon than with the catalyst, the combustion type oxidation. And it has a very low detection limit, making it ideal for bottled water since it ended up being cleaner than tap water. Bottled water typically may be cleaner than tap water. So again, that's good to know that, when you spend that dollar on that bottle of water, you might actually be getting something that's cleaner than coming out of your tap. There's a large disparity in TOC content in the different brands. So the brand matters, maybe, perhaps you can conclude that. And reverse osmosis and vapor distillation for this study technique yields the lowest result of TOC, which you could indirectly say made it the cleanest bottled water. Of course, there's other factors too. And then analysis was done by the Fusion because it has lots of software features to make workflow easy. We talked about auto calibration and teledilution, all those things to make it easier for you so you're not prepping standards all day and that kind of stuff. It easily achieved the accuracy and precision requirements for this study. And then before we go to questions, I just kind of wanted to leave you with this thought. So I did want to note that bottled water has different quality testing criteria than tap water. So tap water is tested against EPA standards, while bottled water is tested to FDA standards. So they're in a different, category. They have different standards. But unfortunately, in our research, we couldn't find a regulated TOC content for bottled water. Although some of the brands voluntarily gave a TOC level, like if you go to their website, they want to say, our TOC level is less than this. They want to show that it's very high quality, it's very clean. So some of them voluntarily disclose this information, although they're not required to. So should there be a required TOC measurement reported for bottled water like most states do for tap water? So that's just a thought I wanted to leave you with.